We will now consider two different types of confidence intervals around the regression line, y hat equals b0 plus b1x, where b0 is the estimated intercept and b1 is the estimated slope. Previously, we looked at a confidence interval around the slope, but now we're going to look at a confidence interval around the entire line. So the first confidence interval we're going to look at is a 95% confidence interval for predicting the mean given a particular x value. So the idea is that given some x star, which is a given x value, we're going to find a confidence interval around the mean for that particular x star. That confidence interval is going to be given by y hat plus or minus t 0.025 with the degrees of freedom times the residual standard deviation times the square root of 1 over n plus n there being the sample size, x star, that's going to be the given x value, minus the sample mean for our x's divided by n minus 1 times the standard deviation of our x's squared. So here we have residual standard deviation that is part of that formula. Okay, we have a given value of x star for which we're going to look at our confidence interval around the mean. We're going to have in here the mean of our x's. That's a sample mean. And then we're also using the standard deviation of our x's in that formula. And then the idea, say if we're using our heights and weights analogy, is that given a particular height, this would give a confidence interval for the average weight for that particular height. That's one kind of confidence interval. The second type of confidence interval will be actually a prediction interval, a 95% interval for predicting the actual y value given a particular x. So if I'm given some, say, height x star, this interval will tell me the values in which 95% of all weights would lie. That interval is given by y hat plus or minus t 0.025 degrees of freedom times residual standard deviation. So it looks very familiar already. In fact, it's going to look very similar. The difference is going to be that underneath the square root is 1 plus 1 over n plus x star minus x bar squared. I think I missed a squared in that formula, divided by n minus 1 s sub x squared. So the difference between the previous confidence interval and this new prediction interval is that there's a 1 here that's added underneath the square root. And again, this is an interval for predicting a y value, meaning that given a particular x star, there's going to be a 95% probability that the y value, any y value, will be within that interval. So let's look at a couple pictures for our global temperature data below. So I'm going to start with the 95% confidence interval given x equals x star. So you'll see that most of the data points actually don't lie within the 95% confidence interval. So these these dotted lines represent the 95% confidence interval. And of course, most of the data points won't lie within those two dotted lines because this is not an interval that's telling us about the spread in the data. This is an interval that's telling us about the spread in the sample means. You'll notice that the interval is thinner toward the middle of our data set, and then it's wider towards the outside of our data set. So that is a feature of this interval in that in the middle of our data set where we have more data surrounding our line, then we're going to have a better prediction for the sample mean. But as you go to the outsides of our data set, then the 95% confidence interval for predicting the mean is going to get wider. Now, if we look at the second interval, okay, you'll immediately notice that the prediction interval is much wider than the confidence interval, and that most of the data points actually fall within that interval. And that's because this is an interval in which 95% of the data should lie. So we expect for this prediction interval that 95% of data should be within this interval, within that prediction interval. Now, this interval also has the feature that it's wider towards the ends than it is in the middle, but it's a little bit harder to see on this graph. Okay, so in the middle, we do have that it's going to be thinner than it is on the outside, but it's just a little bit harder to see. Okay, so let me make some final observations about these two intervals. And that is that both intervals are wider at the ends than in the middle. And also that predicting y is wider than predicting the mean mu y given x. And that's to be expected because one interval is giving us a sense of where the average of the data points will lie. The other is giving us an understanding of where the data points might lie in general.